Okay, so I want to now do an exercise about proving that the pretty good measurement is a POVM. So first, for doing this, you just need to know what is pretty good measurement. So basically, if you define the set of POVM, if you define the set of this of sum of m prime equal 1 to m cm prime of 1 minus where cm is the code word that you try to encode your message with, where m represents your message, where so the code word is just a collection of the realization of the code word of the message, independent variable, the code variables according to the random code. That's what we call the pretty good or square root measurements. And so we know that this uh, triangle M from a POVM, if we add C0 equal identity minus the sum of 1 M1 to M of Cm being superior to 0. So let me try to explain you a little bit about it. So yeah, basically just it's pretty good measurement. Like, to understand it, you need to think about, like, you have something emitting something, like you have the sender and the receiver. So the sender sent a message M that he encoded into CM, like here you have a message M, and so it goes after to CM, you encode it, and he prepare after the corresponding quantum states, which is CCM, like M prime if you want, and he's sending into a channel. Um, and so in a way that you're encoding part, like here, and after you have a channel, and after you apply the PGM, which is your decoding part. And with this filter being like created thanks to the knowledge of the code words, and then we apply it onto the with a measure with a measure physical measure on the quantum state to know the message. Um, so yeah, basically that's it. Half of the beginning, like an orthogonal states, and so it's impossible to distinguish them at 100% at the beginning, but after, um, like, because they can, like, be on one on each other, but when you apply the PGM, um, it will destroy in a way, um, this mixing and the property of being wrong will not be real. It's like you have at the beginning like one, two, three message, and so you just have the projector of the code words um, that will like that term represents like as when you walk, you have the sand making yourself like projecting you onto the ground, create a subspace about it. The same idea here, going from non-orthogonal to from non-orthogonal to orthogonal state to distinguish between both, and so that's how it works. So yeah, basically that's it. Um, and so if you want to know about psi0 here, it's just like when we have applied pretty good measurements and add all the detector, like it allows you to separate the different messages. But for example, let's suppose you have cat as a message and dog, and here's like big ears, and like here like uh, woof woof, like some code words here and here. But like suppose you have also birds, and you cannot know if there is a bird or not. Like CM allows you to know between the different messages, but like if it is other stuff that is not into it, like you want to to know about the other stuff, and so all must sum to identity. So just take identity and all the messages to create this and have all the information. Um, so yeah, that's basically the definition of the POVM, where we need to have like the POVing, all the POVing is positive definite, and the sum of them being equal to identity. Um, so if we want to prove this, we just need to prove it's superior to zero on summing to identity. So by definition, we have psi of m, which is like p 1 minus over 2 is psi m of p 1 minus over 2, which represent our message that are encoded. And so if you try to prove this is semi-positive definite, you just need to take this, and so you just see that you have this. Um, Sorry, I wrote it too fast. Basically, you have C here, P1 minus root 2, so click for columns, and so it's like P1 minus root 2, C. tiger, because you'd switch the cat, the bird to the cat. This. So this is super to 0 because this is super to 0, and the other stuff too. No, like this, super to 0 too. So like super to 0. So the second thing we want to do is that we brought here for the sum of n is equal n to n, but we also have the case where n equals 0. And so if we calculate for this, we have, we just apply the definition. Just get this because it's just also the definition of the sum of n of m, and so this is just after the definition of the projector, like because we have eigenvalues like there are one in the subspace and 0 everywhere else, like just do like this at the end. So it makes one. And so because the subspace identity is all the space and it's like super to 0. And so after we just need to prove that the sum of POVM is equal to 1. So we just need to prove that the lambda 0 is the sum of m for 1 to m. So lambda m is just at the ends identity minus the sum of m of lambda m. No. Plus the sum of m of lambda m, and that's just equal to identity. So the sum of POVM is equal to identity. And so we just prove that this lambda m is a POVM. So yeah, that's it.